Good afternoon, students. So today we solve problems on Cauchy's homogeneous linear differential equation. So in the last classes we have seen the solution of linear differential equation with constant coefficients where f of x is equal to 0. Okay, so problems on these problems of this type we are also solved, and similarly a linear differential equation where f of x is not equal to 0 means we have solved problems under all the cases, means when f of x is equal to e raised to ax, when f of x is equal to e raised to ax into v, when f of x is equal to cos ax or sin ax. Okay, and similarly when f of x is equal to algebraic function. So in all the cases we have seen the solution. Okay, so now I'm giving you the exercises, problems on this type. So this is exercise. So please take the screenshot of this and try to solve these problems. Okay, so these are all problems based on differential equation, linear differential equation with constant coefficient. So when f of x is e raised to ax, when f of x is e raised to ax into v, when f of x is algebraic function, when f of x is sin ax and or cos ax. Okay, like that all the types of problems are given as exercise. So try to solve these problems. Okay, so these are the answers for these problems. So take the screenshot of this also, so that you can verify your problems after solving. Okay, so now we solve. Today we see what is Cauchy's homogeneous differential equation. Okay, Cauchy's homogeneous differential equation. Now here x raised to n dny by dx raised to n plus a1 into x raised to n minus 1 dn minus 1 y by dx raised to n minus 1 plus a2 x raised to n minus 2 dn minus 2 by dn minus 2y by dx raised to n minus 2 plus dash dash plus an equal to f of x. So where all these a1, a2 up to an all are constants, and here this f of x is a function of x. So this type of differential equation is called as Cauchy's homogeneous differential equation of order n. Okay, so this type of differential equation is known as Cauchy's homogeneous equation, differential equation of order n. Now to solve this equation, so what we do, we convert this equation into a linear differential equation with constant coefficients, which we have solved in the last 2-3 classes. Okay, so we have to convert this differential equation into a linear differential equation which we have solved in the last 2 classes. Okay, so to convert that, what we do, we make some substitutions. Okay, we make some substitutions. So here first we replace all the differential coefficients. So here this dn by dx raised to n, this is replaced by capital D raised to n. and here this dn minus 1 by dx raised to n minus 1, and this is replaced by capital D raised to n minus 1, and similarly here this is replaced by capital D raised to n minus 2, and so on. After replacing all those, we get this differential equation. We replaced all those differential coefficients by their differential operators, and we got, and taking y common, and we get x raised to n capital D raised to n plus a1 x raised to n minus 1 capital D raised to n minus 1 plus a2 x raised to n minus 2 capital D raised to n minus 2 plus so on plus an into y equal to f of x. Okay, so now this is equation 2, whereas this is equation 1. So this is equation 1, and after replacing all the differential coefficients by their differential operators, then we get the equation, and which is known as equation 2. Now in this case we make a substitution. So what is that substitution? Put z is equal to log x to the base e. We make a substitution, put z is equal to log x to the base e. Then x is equal to, by using the properties of indices, x can be written as e raised to z. X can be written as e raised to z. Now differentiating this, okay, with respect to x, then we get dz by dx is equal to differentiation of log x 1 by x. Correct? Okay. Then dy by dx. Now dy by dx can be written as dy by dz into dz by dx. So that dy by dx is equal to, so dy by dz means it is 1 by x. Dy by dz, sorry, dz by dx means it is 1 by x. Already we found this. Dz by dx is 1 by x. Now write dy by dz as it is. Now cross multiplying. So this x is cross multiplied with this term. So x dy by dx is equal to dy by dz. Or we can write this as x into d by dx is equal to d by dz. So neglect this y term, both y cancels. So x d by dx is equal to d by dz. That means x into, replace this d by dx by their operator. So x d is equal to, now this is also an operator, okay, like this d by dx, okay, this is an operator, and here the operator is what? A differentiation with respect to x. So this we denote by capital D. And similarly here this is also an operator. Here the operator is differentiation with respect to z. So therefore let this be denoted by capital D1. Capital D1. Okay. So we prove that x into d is equal to d1, where d1 is d by dz and d is d by dx. Remember these two. Okay. So capital D means d by dx and capital D1 means d by dz. Similarly, we get d square y by dx square. Okay, similarly d square y by dx square. So this can be written as d by dx of dy by dx. Right? So that is, we know what is dy by dx. Already we found that dy by dx is 1 by x dy by dz. Okay. So similarly, d by dx of dy by dx is again same as 1 by x into d by dz of 1 by x into dy by dz. That is what we are doing. So dy by dx means first we differentiate this with respect to z, and then z with respect to z. That is like this. Here what we have done, dy by dx, first we have differentiated y with respect to z, and then dz by dx. Correct. So similarly here, d by dx of dy by dx means first we differentiate this dy by dx with respect to dz. So d by dz. Okay, d by dz. That means d by dz of dy by dx. Okay, d by dz of dy by dx into dz by dx. So that dz by dx can be written as 1 by x, and remaining dy dz of this dy by dx is nothing but 1 by x into dy by dz. So which is equal to 1 by taking 1 by x outside, because we are differentiating with respect to z. So we take 1 by x constant, so 1 by x square, this becomes d square y does z by d square y by dz square. Or we can write this one as, we write this using product rule. We differentiate this, that is first 1 by x as it is, differentiation of this d square y by dz square minus dy by dz as it is, differentiation of 1 by x is minus 1 by x square, and simplifying we get, taking 1 by x square common, d square y by dz square minus dy by dz remains. So like that, x square d square y by dx square is equal to d square y by dz square minus dy by dz. Taking a cross multiplying x square here, so we get this term. Now this is nothing but capital D square. Okay, this will be replaced by capital D square. So we can write this as x square capital D square into y is equal to, now this is a differential operator with respect to z, so we replace it by d1 square, because dy by dz is d1, d square over dz square is d1 square minus this is d1 into y, or x square d square equal to, taking d1 common, d1 minus 1. Okay, so like that we got x square capital D square is equal to d1 into d1 minus 1. Similarly we applying the same technique, we get x cube d cube is equal to d1 into d1 minus 1 into d1 minus 2, and so on. Okay, so like that we obtain all the derivatives, that is this derivative, these are derivatives, substituting all these derivatives in this equation. Okay, all these derivatives, whatever we obtain here, so here x into capital D is equal to d1. Okay, this we have to substitute, and x square into capital D square, this one, and x cube into d cube, this one, and all these we substitute in this equation, and we simplify that, some terms will be cancelled, and finally we reduce the this type of differential equation into a linear differential equation, and then apply the method of solving a linear differential equation with constant coefficients. So that already we have solved in the last two classes. Okay, and then we get the solution of the given differential equation, and after that we write the solution in terms of x, so which gives the final answer. Okay, so now example 1, taking one example. So here solve 4x square d square y by dx square plus 4x dy by dx minus y equal to 4x square. Okay, now this is the given equation. As I already told, so here replace d square by dx square by its differential operator, so that is d square, plus 4x, again here replace d by dx by capital D, minus, taking y common, so it is minus 1, taking y common, which is equal to 4x square. Next, put x equal to e raised to z, then z becomes log x. Okay, then make the substitution, x square d square is equal to d1 into d1 minus 1, and x d is equal to d1, and substitute all these in this equation. So we obtain 4d1 into d1 minus 1 plus 4d1 minus 1 into y equal to 4. Here x square, x we have to replace by e raised to z. So x square means e raised to 2z. So 4 into e raised to 2z. Or again simplifying this, some terms will be cancelled, and it will give 4 d1 square minus 1 into x equal to 4 e raised to 2z. So now, which is a linear differential equation, okay, where f of x is 4 e raised to z. Okay, so then apply that technique. So here replace this capital D1 by m. So auxiliary equation is 4m square minus 1 equal to 0. Now split, this can be split as 2m minus 1 into 2m plus 1 equal to 0. Now the roots are, we'll get the roots as 1 by 2 and minus 1 by 2. So the two roots are real and distinct. So general solution we write c1 e raised to 1 by 2x, 1 by 2 z we have to say. Okay, because here the capital D1 is with respect to, differentiation is with respect to z. So therefore here C1 into e raised to 1 by 2z plus C2 into e raised to minus 1 by 2z we have to write, okay, not x, because here the differential operator D1 is with respect to z, that is differentiation with respect to z. So therefore we write this with respect to here z only. Okay, so now we find the particular integral. Okay, now particular integral is equal to, so 1 divided by 4 capital D1 square minus 1, 4 e raised to 2z. Okay, now here we apply the rule, that is when f of x is e raised to ax. You know that what is that rule. So when f of x is e raised to ax, then we replace capital D by a. A means here the coefficient of z in e raised to 2z. So here a is 2. So here replace this d1 by 2. So which gives 1 divided by 4 and 1 divided by 15, because when you replace this by 2, 2 square means 4, 4 into 4 16, 16 minus 1 is 15. So this 4 divided by 1 to 1 by 15 into e raised to 2z. So this is the particular integral. So when we found this particular integral, then write the solution. So total solution is equal to general solution plus particular integral. So now this is the solution of the differential equation. Okay, this differential equation. So actually the original problem is this one, right? The original problem is in terms of x. So therefore we have to find the solution in terms of x. So for that, what we do, we resubstitute the value of z. Now see here, in this case we have made the substitution, that is x is equal to e raised to z, that means z is equal to log x. Okay, after finding the answer, replace z by log x. So in this case here replace z by log x. Wherever z is, just replace it by log x. So when we replace it by log x, then by using the properties of indices, this takes the form of y is equal to c1 root x plus c2 into 1 by root x plus 4 by 15 into x square. So this is the solution of the given differential equation. Okay, so like that we have to solve the given differential equation. In the same way we have this one, solve x square d square over dx square plus x divided by dx plus 9y equal to 3x square plus sine 3 log x. Again here the given equation, we replace all differential coefficients by their operators, and finally this takes the form of this one. Next we make the substitution, x equal to e raised to z, then z becomes log x, then x square d square can be written as d1 into d1 minus 1, xd is equal to d1. Okay, and replace all these derivative in this equation. So we will get this equation, right? Now simplifying this, we obtain d1 square plus 9 into y, 3 e raised to z plus sine 3z. Now this takes the form of linear differential equation with constant coefficients. So now we apply that method. Auxiliary equation is m square plus 9. So just replace d1 by m. So m square plus 9 equal to 0. So that the roots are m is equal to 3i comma minus 3i. Okay, so two complex roots we are getting. So where the alpha part is 0, that means there is no real part, only we have imaginary part, and for that we write the general solution as c1 cos 3z plus c2 sin 3z. Next we find the particular integral, 1 by d1 square plus 9 into 3 e raised to 2z plus sin 3z. This is the particular integral. Now this is an operator, operate this on 1 by 1, we get this equation. Then to find this one, again what we do, 3 is constant, we take that out, then here e raised to 2z is there, only e raised to 2z, so replace d1 by its z coefficient, that is 2, 2 into 2 4, 4 plus 9, so which is equal to 3 divided by 13 into e raised to 2z. So this is the particular integral of first term. Next consider the second term. So 1 by d1 square plus 9 into sin 3z. Okay, now in this case replace d1 square by minus a square. So here minus a square is minus 9, then this gives 0. So okay, this gives 0. So therefore what we do, we differentiate, we multiply this term with z and differentiate with respect to capital D1. Okay, and we obtain the final solution as z divided by 6 into cos 3z. Okay, so now particular integral is general solution plus pi. So 3 by 13 into e raised to 2z minus z by 6 into cos 3z. Okay, now we replace z as log x, resubstitute the value of z. So z is equal to log x. So then we get the final solution is y is equal to c1 cos log x cube plus c2 sin log x cube plus 3 by 13 into x square minus log x by 6 into cos log of x cube. So this is your final solution of the given differential equation. Okay, so what we do, we convert the given differential equation, that is Cauchy's homogeneous differential equation, into a linear differential equation with constant coefficients. Okay, and after that we apply the method of linear differential equation with constant coefficient and we substitute and we will get the solution of the given equation. So with this I conclude this class and continue in the next class. Thank you.